time to start class now. So I'm gonna share my screen. Just scroll up a little bit. Right, so we're going to learn about distinguishability. So being distinguishable means that you can tell the items apart and order matters. And being indistinguishable means that you can't tell them apart, which means that order doesn't matter, and you're basically just picking things from a group. So I have these two practice problems right here. I'll demonstrate these. So how many ways are there to put four distinguishable balls into two distinguishable boxes? Well, we have four balls and we have two places to put these balls. So basically, we're just having these four balls, and then we have two options for each ball, which means it's 2 times 2 times 2 times 2, and that's 16. So there's 16 ways to put four distinguishable balls into two distinguishable boxes. Now we have to find how many ways there are to put four distinguishable balls into two indistinguishable boxes. Well, this is basically the same as the last problem, but the two boxes, you can't tell them apart. So we're just gonna, so basically what it would be is like in the distinguishable boxes problem, if you have balls A and B in box one, you have C and D in box two, then this means that this would be one permutation. Well, if you had A and B in box two and C and D in box one, that would be another one. But in this problem, if you have A and B in one box and C and D in another box, that would be the same if you switched it around. So we just have 16 divided by 2, which equals to 8. So basically the distinguishability problems, like if you have two boxes, you can just divide it by 2. But if it's 3, it's not going to be the same since there are going to be multiple cases you have to consider. So I have some practice problems that I want you guys to do. Also, when you're direct messaging the answers, can you please direct it to me because my computer thing is not the host, but my iPad is, but I can't receive messages on my iPad. So if you have any answers, you can message it to the one that's not the host. It's not review. This is distinguishability. It's like a new concept that I can build more upon it. So this part is basically like review, but the next part isn't going to be as much review. All right, so I gave you guys enough time to do this problem, so now I'll go over it. How many ways can you put 4 indistinguishable balls into 2 distinguishable boxes? So since the balls are indistinguishable, we only need to know how many balls are in each. Wait, hold on. No. So since the boxes are distinguishable, we need to know how many ways we can put these indistinguishable balls into two distinguishable boxes. So in this case, we can just list the cases. We can put either 0, 1, 2, 3, or 4. This is class 5, I think. So we can put either 0, 1, 2, 3, or 4 balls into the first box. So the 5 options. So box 1 is 0, 1, 2, 3, 4. And then 2 would just have the rest of the balls. And then that means that there are 5 ways. There are 5 ways to arrange the 4 indistinguishable balls into 2 distinguishable boxes. So yeah, how many ways can we put 4 indistinguishable balls into 2 indistinguishable boxes? So first we need to think about how many ways we can put the indistinguishable balls into the first box. So we have 0, 1, 2, 3, and 4. And the other one would have 4, 3, 2, 1, 0. But these two, 0, 4, and 4 and 0, that gets counted twice, and 1 and 3 and 3 and 1 gets counted twice. So we basically only have 4, 0, 3, 1, 2, 2, which means there are 3 ways to put 4 indistinguishable balls into 2 indistinguishable boxes. Do you guys need any questions? Oh yeah, and also when you message the answers, you have to message it to Ethan Xiao, who is not the host. So yeah, let's move on. So I have some more practice problems that I want you guys to do these. And if you have any questions, you can message me or just unmute and say it.
Can you make your other self co-host because it's kind of confusing.
I have to stop sharing my screen for a sec. So I'll just do that real quick. Well, I just changed myself to the host. Let me see if I can still share. Yeah, I can still share. So yeah, now you can message the host now, which is me. All right, let me just. So yeah, can you do these problems real quick? I haven't gotten any answers yet, so can you make sure you're messaging to the right person? My computer is the host now, so I can see your messages.
Is it the one that's host or is it the one that's not host?
It's the one that's host. I changed it back.
Okay.
Oh yeah, sorry about the first two problems. I was supposed to make the first one have the boxes be distinguishable, but I accidentally messed that up. So yeah, just ignore that. Treat it as one problem. All right, so I'll go over these now. So the first two problems, they're the same problem, so you don't have to worry about that. The balls are distinguishable and the boxes are indistinguishable. So we have 5 different balls. Let's name these 1, 2, 3, 4, and 5. So basically what we're going to do here is each ball has 2 boxes that it can choose to be in. So basically number 1 has 2 choices, number 2 has 2. We all multiply these all together and we get 32. But that's not the final answer because boxes are indistinguishable. So due to there only being 2 boxes, we can easily divide this by 2, which means that the final answer is 16. So for the third one, the balls are indistinguishable, but the boxes are distinguishable. So basically what this is that since the balls are indistinguishable, the only thing we need to keep track of is how many balls are in each box. In this case, we can just list the cases. We put either 1, 0, 1, 2, 3, 4, or 5 in one box, and we'll just stuff the rest in the second box. So then there would only be 6 ways to do it. So there's 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, and 5, 0. Keep in mind that the 2 boxes, you can tell them apart. So that means that there would be 4 in the first box and 1 in the second box wouldn't be the same as the other way. So yeah, neither the last problem, neither the balls or boxes are distinguishable. Just erase this real quick. Well, in this one, we only need to count the number of ways to split 4 items into 2 groups. To split 5 items, I mean, into 2 groups. So then that would just be only 3 ways: 5, 0, 4, 1, and 3, 2. And if you do 2, 3, 1, 4, and 0, 5, those are just repeats. Since the boxes aren't distinguishable, you would just be counting everything twice. So then there's only 3 ways for the last one. All right, let me move on. So this one is different from the first one since there's 3 indistinguishable boxes, you can't just divide it by 3 factorial. You have to count all the cases. So I'll just let you guys do this. If you have any questions, you can message me. Yeah, Judy. You raised your hand. Do you have a question, or was that just an accident? All right. Well, I'll go over these now. So here we go. How many ways can we put 4 distinguishable balls in 3 distinguishable boxes? All right, it's fine. So here we go. The first thing is we have 4 different balls that we can tell apart. 1, 2, 3, and 4. And we have 3 boxes that we can tell apart. All right. We have these 3 boxes that we can tell apart. 1, 2, 3. So we have to put all of these 4 boxes into 3 box and 4 balls into 3 boxes. So each ball has 3 choices, right? So that would be 3 times 3 times 3 times 3, and that would equal 81. And since the boxes, you can tell the boxes apart, which means that you can just have 3 choices, 3 locations for each ball. So it's as simple as that. Now, how many ways can we put 4 distinguishable balls in 3 indistinguishable boxes? So first off, this is a lot different from the first one. You have to consider all the cases. Since each case, you have to divide it by a different number. So here we go. Since the boxes are indistinguishable, Jason, you just raised your hand again. Was that an accident? Okay. All right. How many ways can we do this? So since the boxes are indistinguishable, there are only a few different cases we can put everything. So since we have 4 balls, we have 3 boxes, we can list out all these cases. So we have 4, 0, 0, which means we put all 4 into one box. We have 3, 1, 0, which means we put 3 of the balls into one and one in another one. And we also have 2, 2, 0, which means we put 2 in one box and 2 in another. And then we have 2, 1, 1, which means we put 2 in one box and then we just have 1 for the other 2 boxes. So we have to consider all these cases. So first off, we have 4, 0, 0. Since we're putting all the 4 balls into one box, right? So we only have one way of doing this since you can't tell the boxes apart. So the first one is 1. You have to add all of these together. So now we have 3, 1, right? And we have the 1, and since we can tell the balls apart, that means that one ball would be different from the other 3. So since we have 4 balls, there's 4 ways to do this, since we're basically just choosing 1 from 4. And next we have 2, 2, 0. And since we're choosing 2 from 4, that means that we have 6 ways of doing it. And now we're going to do 2, 1, 1. This one is pretty difficult, but let's just choose 2 of them for the first one. So there are 6 ways to choose. There are 6 ways to choose the first 2, and now we have to balance the other ones around. So that means that there are 2 other ways to put the 1 in 1. So that means that there would be 6 times 2, which is 12. So then we add these all together and we get 23. So there are 23 ways to put 4 distinguishable balls in 3 indistinguishable boxes. So basically what this is, you have to consider all of the cases, and then you have to find a number of possibilities for each case. So it's like casework, but you're like finding combinations. So yeah. So for a summary, you can't divide it by 3 since each case has its own number you have to divide it by. So like if you divide it by 3 factorial, you see the first one we have 81. If we divided it by 3 factorial, we wouldn't get an integer, which means, so we know that we have multiple different cases that we need to consider. So, and for the other one, since it's only 2 boxes, there aren't really that many cases. There's only 2, so you can just divide it by 2. So summary, combinations can be used to compute the number of paths on a grid, like we did last week, where we just chose the number of ups and stuff. We may have to combine our earlier counting techniques with our new knowledge, like when we used casework for the last problem. Distinguishability matters, and it's really important, since if you don't consider like if something's distinguishable or not, you're probably going to get the problem wrong. All right, so let's move on to the next unit, which is some harder counting problems. So in this unit, we'll look at some more difficult problems, and we'll apply everything that we learned so far in order to solve these problems. So in a bowling tournament, 8 bowlers are ranked 8-1. First, the 8th bowler plays the 7th, and then the 7th, and whoever loses is ranked number 8. Then the winner plays the 6th, and the loser is ranked 7th, and so on and so forth until the winner of the second one plays number 1, and whoever loses is ranked number 2, while the winner is number 1. So how many different outcomes are there? Well, at first this might seem hard, but then you realize that there are only 2 possibilities for each place. So if you have like place number 8, you have the number 7 and number 8 who are playing each other, and whoever gets the lowest score gets number 8. So there's 2 possibilities for each place, since 2 people are playing a match and the loser gets that place. So we basically have 2 times 2 times 2 times 2 times 2 times 2 times 2, since there are 8 places, but the first place just gets whoever is not the second place, so that doesn't really count. So we just have 2 multiplied by itself 7 times, and the answer is 128. So a lot of these you need to apply like critical thinking and stuff, and finding an easy way to solve these. So I have some more problems for you guys. I'll let you take some time to do this. And if you guys don't get the problem, just tell me that you don't get it, and I'll go over it in a few minutes, so don't worry about that.
I don't really get it.
All right, that's fine. I'll go over it in a few minutes. All right, I'll go over number one since a lot of you guys are confused on this. So let x equal 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, which is writing all the integers from 1 to 999 beyond the decimal point. What is the 2005th digit to the right? So basically, we're going to consider all the cases here. So first we have 1, 2, 3, 4, 5, 6, 7, 8, 9. The numbers 1 through 9 only use up one decimal point. So once we write through 1 to 9, we already used 9 places. And now we have to consider the numbers with 2 digits. So from 10 to 99, that is 90 numbers. So we have 180 decimal places. So 9 plus 180. We have used 189 so far from 1 to 99. So now we have to consider 100 through 199. And that would be 300. And we know if it's 100 through 999, that's too much. So we're just counting by hundreds now to narrow it down. So the first 100 gives 489. The next one gives 789 for 200. From 100 to 200. Then from 200 to 300, that's 300 more, 1089. And so on and so forth until we get to 699, which is 1989 decimal places. But now at this point, the 100, but now we can't go any further since if we add 300 more, that would be too much. So the 1990th digit is the first digit of 700, which is 7. And since we want the 2005th digit, we just subtract the 1989 from that and we get 16. So we want 16, we want the 16th digit from 700. So we start with the 7 from 700. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this 7 is the 2005th digit of 7 is the 2005th digit of the first number. So yeah, that's the first problem. So as I went over this, we just basically covered 1 through 9. We counted the number of digits for each set of numbers. Yeah, 7 is the answer. And then we narrowed it down to the place closest to 2005. And then we just like solve it from there.
What's in
What?
the second problem?
If you don't understand that, I can go over that soon.
Because it doesn't define what in is.
Yeah, you have to find n. All right, so let me just go over the second one real quick. 9 parallel lines in a plane intersect a set of n parallel lines that go in another direction. So the lines form a total of 360 parallelograms which overlap each other. Find n. So what they're talking about is here, like if you have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, we can have some lines that go the other way and it would form these parallelograms. So basically that's what it is. Now, since the lines form a total of 360 parallelograms which overlap each other, we need to find an expression for the number of parallelograms in terms of n. Then we can set that equal to 360 and solve for n. So how do we create a parallelogram by choosing some of our lines? We need to choose 2 lines from each set. This will give us the 4 sides of a parallelogram. So if we like just choose, say, 1, 2, then we just choose some random lines here, then these 4 lines would form a parallelogram. So we need to find the number of ways we can choose these lines. So the number of ways we can choose 2 lines from n, no, the number of ways we can choose 2 lines from 9 is 9 choose 2, which is 36. And we need to see how many lines are on the other side so we can choose 2 random lines. And there are n lines, so the number of ways we can choose that is n over 2. And now since there are 360 parallelograms, and we know that choose 2 from 9 is 36, we need to set choose 2 from n equal to 10. So basically, we can just see that, but we need to see, some people can solve this just by looking at it, but other people need algebra for this. So we can write out the formula and set it equal to 10. So n minus 1 over 2 equals 10. So now n minus 1 equals 20, and you can find from here that n equals 5. So the second answer is 5. All right, let's move on. I have some more demonstration problems here. So I want you guys to do these. These are like all problems that'll test your knowledge. So and these are also really hard problems. So if you don't know how to do them, that's fine. Yeah, number one should be an equation. All right, so I'll go over these problems right now. So Janie is a house painter. She has been given a contract to paint any K of the houses that she wants on a street with N houses. She has J different colors and uses one color for each house. So how many ways can she paint the house? So imagine that you are Janie. What's your decision process? First, you have to choose. First, you have to choose which K of the N houses that you want to paint. So since it doesn't matter which order you paint the houses, um, the way we can choose K from N, we can just write it like that. And second, for each of the K houses, Janie has to choose one of her colors to use. The choice of color for each house is independent of her choice for the other houses. So to get the total of number of ways that she can choose colors, we multiply the choices for each individual house. So then that means there are j to the power of k ways to choose colors once the houses have been chosen. So then we just do this. And since for each of the n choose k ways to choose the houses, Janie has j to the power of k ways to see how many times she can paint. So yeah, that's the answer for the first one. It's a fairly simple equation. Now for the second one, Spiffy the spider has 8 legs, each of which is a different color. Spiffy has a sock and a shoe for each of his legs, so that he can has one sock and one shoe in each of the 8 colors. The letter that's K. K is the houses that she wants to paint. Well, the number of houses is n, so technically it's not infinite, but like it depends. So then it would be n. Spiffy the spider has 8 legs. And how many ways can Spiffy put on his socks and shoes if each sock and shoe must go on the leg with the matching color and the sock goes on before the shoe? So basically here, this may seem complicated at first, but if we solve a simpler version of the problem first, you can go and use the same method on the harder problem. So first we're going to pretend that we have a person and that person has 2 legs, right? So they have one sock and they have one shoe that they must put on each of their legs. So you have a left sock, a left shoe, a right sock, and a right shoe. How many ways you can put on your socks and shoes if each foot sock must go on before the shoe? So let's think about it. So the number of ways we can just put these things on randomly. First, we need to find all of the ways you can put everything on. So we basically just have 4 factorial since there are 4 items. If we just put these on randomly, which is 24. But since some of these things aren't allowed, we can focus on each foot first. So we can eliminate all the possibilities that she puts on the left shoe before the left sock. And since that is basically that's going to be exactly half of them, that means we just divide this by 2, and that's 12. But now we need to find the ways she puts her right shoe on before the right sock. That's also one half. That's also one half of the ways. So we divide it by 2 again, we get 6. So for someone with 2 feet, there's 6 ways you can do this. Now, basically, we just do the same problem, except the spider has 8 legs. So now we have 16 things they need to put on. So 16 factorial. And now we need to get out all of the ways that the spider can put on the shoe before the sock. And since there's 8 feet, that means there's 2 to the power of 8 ways we need to divide it by. So we just do that, and our final answer is just basically this. Yeah, I know. But the final answer is going to be a very large number, 81,729,648. 729,648,000. So yeah, that's a lot of ways. But basically what this problem is telling you is that if you have a really hard problem, you can just do an easier version of that problem and then just solve it like that. Use the same method on the harder problem. He has to put the sock on before the shoe, so that just takes out a lot of the ways you can do it. Alright, so the summary is, when you're stuck on a problem that gives data in terms of variables, plug in some numbers and solve it and look for a pattern, like what we did for the last ones. When you're unsure how to approach a hard problem, try to solve a simpler version and then do the hard one using the same method. And be flexible. Don't just use one method. You should try all of them. We learned a lot of things like probability. No, we learned complementary counting. We learned like combinations and all that stuff. So yeah, class is over for today. I'll see you next week. Bye.